Statisticians, welcome back to another riveting installment of your AP Statistics journey. Today, we're going to be looking at least square regression lines and where they originate from. Ideally, by the end of today's video, you'll be able to calculate and interpret a residual, slope, and y-intercept of a least square regression line, so you can make predictions using those regression lines, keeping in mind the dangers of extrapolation. I'll know I've got it when I can determine the equation of a least squares regression line using technology or a computer output. That'll come in a few lessons. All right. Quite often throughout the history of the United States, we have struggled with an income achievement and income attendance gap. Nationally, low-income students perform worse on math exams and all exams than their middle and upper class counterparts, and low-income areas have more chronically absent students. Could we say that there exists some correlation? Let's find out. Policymakers, the wealthy, those that think they know how to fix systemic issues in society, applied this Band-Aid to a bleeding wound. The way you close the achievement gap, that's easy. Get them to school. Increase the attendance rate. It'll magically fix their performance. So today we're going to be looking at, do schools in America effectively equalize opportunity for low-income students? And will raising attendance also raise scores for low-income students? The rhetoric, as I had just mentioned, goes like this. Those who exist in poverty typically experience low rates of attendance to school, which subsequently lead to low scores on performance-based assessments. Those that design policy measures say, well, if we somehow fix the attendance problem and we change it to high, let's put that there. And so basically, those that grow up in poverty, if they can just attend school at a very high rate, then they will magically have very high scores. I wonder what you think about this. Let me know. What do you think? Do you think increasing attendance would close the achievement gap or not close the achievement gap? And then share your thoughts. So to take a look at this data, we're going to take a look at a random sample of Texas students. Data was collected on the percent of school days they attended and their school on the Algebra 1 state exam that year. I'd like for you to first identify which variable is the explanatory variable. Remember, an explanatory variable is the variable that explains the response from the other piece of quantitative data. I've now taken that data in the previous slide and created a scatter plot for your reference. Next up, so that we can constantly sharpen our skills, I'd like for you to describe the scatter plot using our CDOFS acronym. I've given you a bunch of different choices here, so please select the ones that you think would apply in this regard. And now into the meat of what we will be talking about for this video. So the superintendent, right, based on that data that we have generated here in the scatter plot, wants to know what the predicted test score would be for a student who meets the minimum attendance goal of 87%. I'd like for you to spend some time here fitting the best orange line you can to this data. Now, obviously, we can't necessarily catch all the points, but we want to create a line that's going to catch as many as possible. So something you might have noticed is as you manipulate the orange line, you might have made continual adjustments until visually you felt, yes, I've captured as much of the data as possible. What was your thought process in doing that? What were you specifically trying to accomplish with your orange line in relation to the green dots? Meet the residuals. They're like the Eternals in Marvel, but statistical superheroes. Residuals are the distance in the response variable between each data value and its predicted value in our linear regression. In layman's terms, looking at our two least square regression lines here, it's the distance between our blue specific data values, right, the scatter plot itself, and the line that we've generated that maps as best as possible the behavior of the data. So the least square regression model is the line that minimizes the sum of the residuals because we want to make sure that our line is as close as possible to these data values. So the manner in which we accomplish that is we take our data value, our data value, and we subtract the predicted value. The way that we do that, I'm gonna have to fast forward a little bit just to grab a character. There you are. Copy. So statistically, it's written in this manner. Y represents the data value minus y hat. Y hat is the predicted value from the least square regression line. Squared residuals between the data and the model, sometimes referred to as the line of best fit. So let's say, for instance, that we had a data point here. Let's say that this data point was 7.5, this blue point, and let's say this predicted value here was 7.3. As you can see, the distance between the data value and the predicted value, this would become a distance of 2. Seems to be, rather small. Obviously, taking a look at data values like this, these are ideal, but that is not necessarily the case considering on how spread out our scatter plot data is. Now, here we have a very good representation of what is ultimately unfolding within our residuals. So what you're going to do is you're going to take these two dots, and as you move these two red dots, you should be able to see that the distance or the residual is changing. Sometimes it's getting larger in that case, but ultimately we want to create it so that it gets as small as possible. And I have a counter over here that's doing that for you and calculating the total area of the blue squares. I challenge you to get it as low as possible. Whoever obtains the lowest residual value here will receive some extra credit. And at the same time, we're generating an equation for your line based on what you're accomplishing. Okay, so you should have just seen how low you could possibly go. But once you're ready, move on to the next slide. So here is the line of best fit or our least square regression model. Y hat equals negative 7.689 plus 0.567x. Now, this is every mathematician's favorite one-liner, and that is y equals mx plus b, slope, intercept. So there are a few key differences, but structurally they are the same. So back in the day when you were a Algebra 1 phenomenon, y represented a data value. Now y hat represents a predicted data value. M was the slope. Currently, that is b. For b was the y-intercept. Oh no. We're going to go y. I will fix this. So y in, go like that. And a now represents the y-intercept as well. So in the previous slide, we've taken the structure of the least square regression model line and applied different components to it. The more challenging aspect is interpreting those components in context. So first and foremost, anytime we have an LSRL, we want to make sure that we identify what is our explanatory variable, percent attendance, and what is our response variable, predicted test score. So this slide, I'm going to challenge you to generate two responses to these questions. How do we interpret the slope value in context, and how do we interpret the y-intercept in context? I provided stems here that you should follow when crafting your response. So for every 1 unit increase, the unit that we're using, increase in explanatory variable, that's percent attendance. Our model predicts an average, and I'll let you take it from here. Now, if you go back to the slide from 2 ago, the axis is cut off. So it is difficult to determine what the y-intercept is. However, you should be able to determine what the y-intercept is from this equation, which is what you're going to need to do before you generate the y-intercept in context response. So is that meaningful or is it not meaningful? Once you select, you'll come to see it's not meaningful. But why? Why is it not meaningful? Here, we're going to go back to our Algebra 1 days, and we're actually going to answer that superintendent inquiry. So the superintendent wants to know, when a student meets 87% attendance rate, what will their predicted test score be? I'd like for you to identify this on the graph. So please make sure you identify that corresponding location on the predicted value. And then you'll need to generate some algebraic evidence. Remember, you can just copy and paste the equation rather than typing it yourself. You can just press Control C and then work from here accordingly. Remember, think through what represents X, what variable represents X, and what variable represents Y. And then just finish our sentence here for us once you've done that. Now, the dangers of prediction. Our response on the previous slide incorporates the word predicted. That is very important since a student who has an 87% attendance is not guaranteed to get 41.9 points on the state test score. Hint, hint, that's the answer to the last slide. In fact, it's impossible to get 41.9 questions correct, but we do predict that they will get about 41.9 points on average because, listen, things go wrong. That's our world. So why is it so important to use the word predicted when writing a response sentences about the response variable in regression? Now, let's talk a little bit about what has been done, right? So in the past few years, decades, superintendents have piloted a ton of different initiatives they've done for specific programs in-house for chronically absent students. They've hired attendance officers and case managers and coordinators, and they've even contacted Uber and Lyft trying to help students get to school. So consequently, yes, attendance has, without a doubt, gone up. So subsequently, the more you're in school, yeah, you should be doing better. However, test scores, for the most part, have not risen significantly, and the achievement gaps have remained. Why? What happened? Why didn't the test scores grow when attendance rose? Because according to a lot of wealthy, intelligent people, that's the MO. High attendance, high scores. Because low attendance, low scores. That's how correlation works, right? Or maybe it doesn't. I don't know. You tell me. But we'll pick up this discussion in class. See you there.